Okay, well, so first of all, I'd like to give credits to Professor Somil Bansal. He's a professor at University of Southern California. He was a PhD student of UC Berkeley when he worked on this. So I kind of happened to be in contact with him, and that's how I got to know about this whole topic of Hamilton-Jacobi reachability. And as you see, I'm quite lazy enough to prepare my own slides, so I'll be reusing his slides. So I hope there is no copyright issues. But I don't think so. I'll talk to him. So I hope you've gone through the paper, at least some parts of it. So we'll start uh, with the premise of the problem. Just a second. So yeah, this is the outline that the slides, and I will be following. I might skip through some parts because some parts might be irrelevant, but I'll give you a basic idea of what an optimal control problem is and what exactly is reachability and how does it come into picture while solving optimal control problems. Optimal control problems are practically everywhere, be it finance, be it physics. It's practically everywhere because we as humans like to have authority over things, right? We love to control people. So, an optimal, not control people, control things. We also love to control people, but there's a different angle to it. So, optimal control is everywhere, and it's a very widespread problem. And again, there's a lot of literature on it. We'll be focusing on the reachability aspect of it. So this is the outline that we are going to follow in the slides. So yeah, reachability. So again, as it's practically a reiteration of that, what I've just said. So what exactly is an optimal control problem? So for example, suppose you want to reach, so I'll try to, like, this is the example, this is the slide, but I'll try to explain it via the Jamboard. What exactly is an optimal control problem? So for example, this is point A and this is point B, suppose, and you want to reach from point A to point B. There are various different trajectories. Okay. So for example, suppose there are four trajectories, point from here, 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 and here. And obviously you're taking a car, so you'd want to spend you want to spend the least amount of fuel because obviously you want to save money. So you want to reach from point A to point B while wasting minimum fuel. So this is practically an optimal control problem. So how would you get there? So for example, your car gives a mileage of around some x kilometer per liter, I guess. So okay, this Jamboard is a bit clumsy. I won't write all those things because it might take a lot of time. So your car gives a mileage of x kilometer per liter. So what kind of trajectory would you choose? Can anybody answer this question? It's a pretty simple question. I mean, it's practically speed, distance, and time problem from your grade 7 maths textbooks. So, for example, if you're given the mileage of your car, what kind of trajectory would you choose? It's a very simple problem, guys. Can anybody unmute and answer this question? A simple question.
The second one.
Yeah. Hello.
The
Yeah.
one with the
Second
least
one.
distance.
Yeah.
Yeah.
Second problem.
So, are you trying to say that the path where we have to cover the least amount of distance?
Yes, yes.
Exactly.
Okay.
So yeah, it's quite simple. Yeah, I mean, a lot of you guys do computer programming, so you'd know better what kind of paths we would use. I won't know that, but yeah, it's there. So you're absolutely correct. But suppose there are certain obstacles too in this path, in all the paths, and to like suppose there are certain molehills, there are certain stones, there are various obstacles. That's it. And to overcome these obstacles, a certain amount of fuel is wasted on a particular path. So, for example, so again, you choose the path where the distance is less, so you waste less fuel according to this mileage that you're getting. However, suppose that path has a large number of obstacles, and these large number of obstacles consume a lot of extra fuel to be overpowered. So you won't choose that path, right? You would want to choose a path where the net sum of where the fuel consumption is minimal. So can I say that there are two aspects to an optimal trajectory, right? One is this mileage, that is the running cost. For example, I'll call it running cost. That means it changes as a function of time. But these obstacles are fixed for a particular path. Okay, are you all getting it? These obstacles are fixed for a particular path, and to overcome these obstacles, a certain amount of fuel is required. So there are three obstacles, and each obstacle takes, suppose this one takes x1, this one takes x2, okay, and this one takes x3 amount of fuel. So the net fuel consumption for this trajectory is x into d. D is the length of this track, plus x1 plus x2 plus x3. And this x1 plus x2 plus x3 is constant for this path. It won't change with time. So this is the perhaps the intrinsic characteristic of the path itself. So this is what I'm getting at. So now we come back to the equation aspect. So what exactly are we trying to do here? We're trying to choose, in this case, we're trying to choose a trajectory where the net cost is minimized. And net cost would not only depend on the running cost, but on the trajectory itself. So the optimal trajectory would be the one where the sum of this running cost plus the sum of the cost, sum of the fuel consumed by the obstacles, that is what I would like to call the terminal cost, would be minimum. So let's go and see the expression. You can ignore the discrete time expression. In fact, practically you can replace the summation and integration to switch between continuous and discrete time systems. I mean, it's quite clear. Most of you have taken, I think, the preliminary mathematics course, so you would know that. So I'm not going to get into that. So what am I getting at? Getting here is that, see, we want to choose a trajectory for which this running cost, c is the running cost. For the time being, we can ignore this notation x and u. Don't look too much into it. I'll explain what is a state space and how do we infer things out of this. But for the time being, let this be. And again, can someone looking at this equation, u is the control action. Looking at this equation, can someone say what is the equation of a state here? Like it's a simple equation. Okay, let it be for the time being. I'll get past it. So yeah, can you actually correlate between the example that I gave and this and whatever and the expression here? This expression, that is the cxtut dt, is the running cost. That is for a given time frame, we are going for a certain distance, and it is the cost accumulated over that. And this lxt is called the terminal cost. This lxt is, I mean, the kind of the trajectory that we have taken, this lxt would be fixed for that, for over the time horizon. So can you actually correlate? Hello?
The C refers to the obstacles, right? And the LXT is actually the path. That,
No,
or
it's actually the reverse. Can you, if you notice, c varies with time. That means the more we are traveling, the more distance we are traveling, the more cost we are
oh,
accumulating.
right.
However, this is the fixed component.
Yep,
So
yep.
for example, in this, suppose we travel d distance, like we reach b, and the distance of this path is d. So can anyone tell me the cost accumulated? There are three obstacles with each with the cost of x1 plus x2 plus x3. So can anyone tell me what is the terminal cost? It's a simple speed equation. D is the distance. Like suppose, okay, t is the time. T is the time that we have traveled upon that path, reached. So can anyone tell me what is the cost on if we take the first path? The speed is x, the mileage is x, and the distance is d, and the time is t.
integration of xt plus the obstacles that are there.
Yeah. So it's exactly that thing. And integration of x dt is the integration thus the cost that we would be incurring is practically the mileage, right? D would be the distance that we have covered. D by x would be the amount of liter of petrols that we are wasting, right? And into the C, the cost of per liter of petrol. So can we agree that D by X into C is our running cost for this whole trajectory?
Yeah.
Yeah. And can we agree, for example, there are three obstacles. Can we agree that X1 plus X2 plus X3, like X3, okay, is the terminal cost of this trajectory?
Yes.
Yes.
Yeah. There is a notation of time. I'm just trying to give you an example where you can understand the running component and the fixed component. So what is our original goal? What our original goal is to choose a trajectory such that the net value, the net summation of these two costs are minimized. Okay. So I hope you got that thing. Let me erase it. It's now. So I think so. You got the gist of an optimal control problem. I would come to the time horizon and all the other aspects of it, but like for an optimal, you got the gist of an optimal control problem. There are two components to an optimal control problem. That is the running cost and the terminal cost component of it. So yeah, okay. This erasing the Jamboard is a bit irritating, but I guess.
Maybe you can try
Yeah.
the clear
There's
field.
an clear
Oh,
field.
there's that. Oh yeah, that's there. I've not used Jamboard. So yeah. So we got it right. So I think we are on board till now. I hope I've not lost all of you. So you can see there are two components. I'm trying to encircle it via my cursor. This is the running cost component. This is the terminal cost component. Okay. Now, I'll come back to this one later. This is not relevant right now. Huh. So so again, practically so again, now I'll come to the state space and other notation aspects. Okay. So for example, does any one of you have a bit of an idea of of how can we yes, how can we represent a dynamical system or a simple system? Like for example, this is okay. Okay, I'll give you the required background. So suppose this is the equation that we generally use in our optimal control. I guess. So this is the expression that we'll be, this is the generally, this is called the state space equation. I'll give you the notion of a state. So ideally, I think the electrical guys would understand it after fifth sem. I don't know about the computer science and other people, but I'll give you the, for example. So X is practically a set of vectors with which we can characterize our state. Okay. It's there. It's a set of vectors with which we can characterize our state. For example, so for example, in the previous example, in the previous example that I gave, uh, can we say, hmm, okay, let me just reiterate over it. Let me just get over there. Hmm. So for example, we can take our state space variables as anything. Generally, the memory elements is kept as state space variables, but we can keep the state space variables as anything. However, the state space variable should be chosen such that we get the overall information of the system. So in the previous example, in the previous example that I gave you, point A to point B, there are various different trajectories. If we know, like, what is the state space, if we know the velocity of our particle, I mean of the system, or maybe let me reformulate it and give it an example. Like, okay, I'll avoid this example as a whole. It's a bit limited. I'll take a different example. So, can you see this? So, okay, let me just see. So this is a tree, okay, and this is a circle of around perhaps 0.5 meter, 0.5 meter around the tree, and we have a car, that is moving. I mean, not exactly moving towards the tree. No one is. If we want to avoid a tree, what kind of information do we need? Okay, just take a simple guess.
Hello, can you repeat the question? Like I was absent for like
Uh,
1 minutes.
yeah. The question is this: there is a tree, and ideal. Okay, let's avoid this radius thing for a minute right now. There is
So
a
this is a
tree,
tree.
and there is a vehicle that is moving towards the tree, not exactly towards the tree, but is moving in the direction of the tree. And we would not like the vehicle to collide with the tree. So what information do we need so that we get an idea of whether the vehicle will collide or not?
The direction of the motion of the vehicle.
Yeah, the direction of the motion of the vehicle. Okay. And if I add one more component, like for a certain time duration, 0 to t, suppose the vehicle will operate only in this time horizon. This is called the time horizon. It's practically the time limit in which we are trying to control the vehicle. So in this time horizon, we would like to avoid the tree. So the direction of the vehicle is is one aspect, and the other. In this time horizon, we would not like to we would like to avoid the tree. So
Velocity.
yeah. So if we are given the velocity, and if we are giving the velocity and the direction in which the vehicle is heading, we can actually we can actually infer whether the tree will collide, whether the vehicle will collide with the tree or not. So that's what you're getting at, right? Exactly. And how would we know whether whether the vehicle is in danger of colliding with the tree or not? We can do one thing. If it gets in a certain radius of the tree, like a small radius, for example, if it gets in a radius of r, like for example 0.5 meter within the tree, we can actually say that yeah, it is in danger of colliding with the tree. So we can say the distance, we will keep the tree as the origin. We can say that the distance of the vehicle from the tree is our state space, and the evolution of these distances, like x comma y is the coordinate of the vehicle, and would tell us the distance. So if we know the the coordinates of the vehicle itself, we would know what state the vehicle is in. So for example, we would not want the vehicle to get in a 0.5 meter radius of the tree just to be on the safe side. So can we say that if it is outside this circle of 0.5 meter radius, our vehicle is in the safe zone? Okay. Are you all getting it? I, I'll assume that you all are getting this. So yeah. So if it is in a radius of 0.5 meter of the tree, if it is in the radius of 0.5 meter outside the tree, that outside this circle, we would assume that it is in a safe state. However, if it gets in this state, we'd be alert and we would get to know, and we'd be alert and we would know that the tree is in the danger zone, that the vehicle is in the danger zone now. It might collide with the tree. So can we say that the distance of the vehicle, from the tree itself would tell us the state in which it is in. So if it is at a distance of 0.5, 0.6 meter, it is in a safe state. And if it is in a radius of, if it is in a, if it is at a distance of 0.3 meter and 0.4 meter, we can say that the vehicle is not in a safe state, it is in an unsafe state, and we need to take some other action. So can we say that x comma y is our state space variables by which we can characterize whether the tree is in a whether the vehicle is in a safe state or an unsafe state? Can anyone answer, like, yes or no? Are you all getting this? Like, if I specify the x comma y coordinate, I can actually specify, if I can actually if I specify the x comma y coordinates of the vehicle, I can actually tell what kind of state it is in. If So this is the point. So
Yes,
x comma y, yeah, x comma y is the x comma y, that is the coordinates of the tree, is our state variable for this system, x and y. And the evolution of these two variables, like, can we write it as x dot, like velocity in the x direction as v cos theta. Theta is the radial angle at which it is coming. As Ayush told, the direction, theta would tell us the direction, and v is the velocity. So can we say that if we have this information, we can actually tell whether a tree would whether the vehicle would collide with the tree or not? Can we say that?
yes, we can say that.
Yeah. So if we know about the velocity and the theta and the evolution of the state space variables with time, we can say that we can predict whether we can actually try to predict whether it will be in an unsafe state or a safe state. So this is the whole point. Can you see there is a derivative term involved? That is the evolution of the state space with the time. So that equation is just that. X dot is equal to f x comma u. This is the equation. X dot is the state space vector. Like, for example, x the derivative of the state space with respect to time. So the x dot vector is practically this, x dot and y dot. Shall I use a different notation, or are you getting this? This is a capital X. So this is the state space. This is the x dot practically tells is the derivative of our states of all the state space variables with respect to time. That is, it tells the evolution of our state space with respect to time. And f is the function with which our state space is varying. So for example, we can say that f here is this matrix, v cos theta and v sin theta matrix. And I'm coming to u is the control. So for example, if I am the driver of that vehicle, if I get to know that I'm in an unsafe state, I'll try to steer the vehicle, right? I'll try to control the velocity and the angle and the direction in which it is heading. So in this case, the control that we have is the velocity and the theta and the direction. So u is the control that we can apply to change our state space. So this state space equation practically So this is the state space equation. I'll rewrite it again. This is the state space equation. It tells us the evolution of our state space with time, and how can we control it to reach the desired state that we want. Are you all getting it? So it's a function of the state space itself, like, and the control that we are applying. So did you get the state space equation?
Yeah.
Yeah, you all got it. Okay. So this is the state space equation. Now I think we can go there. So now I think you can read the notation better. J is the cost function. This is the running cost. This is the terminal cost. Now, what do we want to do? We want to minimize the cost. We want to minimize the cost. So what do we want? We want the control, that particular control. We want to minimize the cost, and what is our domain? Our domain is the set of all state spaces that we have, state variables, and the set of all controls that we can apply. For example, in the tree example, the control that we can apply is that, for example, velocity, our car can't go beyond a velocity of 60 kilometers per hour. So the control that we can apply over the velocity is 0 to 60. And suppose we can steer the theta in any direction that we want. So the control that we can apply over theta is minus pi to pi. Okay, I hope I'm getting it. I hope you all are getting it. Oh, man, writing on this is a nightmare with a keyboard, with the mouse. So yeah, so this is the set of states from which we can choose our control actions from. So for example, if I choose a velocity of 3 kilometers per hour and I choose a direction theta, that is 90 degree. That means we are moving at an angle of 90 degree towards the tree with a velocity of 3 kilometers per hour. So this is the control. So what is our objective? We try to choose such a control action, such a control would minimize this cost. So I hope we are getting there. And I think I wasted a lot of your time on just setting this on this setup only. So yeah, now I think we can come there, come on the main part. Okay, calculus of variation aspect, we can skip past it. So how many of you know about dynamic programming? Can I assume that most of you all know about dynamic programming? Think I can assume that. So I'll move past it. So for example, what does the principle of dynamic programming actually state? In the context of optimal control problem, what it is trying to say is that the optimal state trajectory remains optimal at intermediate points in time. It's not like, for example, if I take this trajectory to reach there, if I take this trajectory to reach there, if I take this trajectory to reach there, it doesn't mean that for if I want to reach here at this state, it doesn't mean that we can take a non-optimal trajectory here. Like, for example, let's take this. Let's take the same example. You want to reach A to B in the minimum possible time. Your velocity is constant. Okay, there are various different paths. We all know that we'll take the straight line, but okay, I'll take an instance. Like, for example, if we want to reach A to B in given path, so can we decompose it in 3 steps? For example, I would try to decompose this problem into 2 more states. I would reach from A to C, C to D, and then D to B. Okay. So these are the states that we are in. Again, I think the figure is not very clear. So what the principle of dynamic programming says that we can't take a non-optimal trajectory from A to C, then some another optimal some other non-optimal trajectory from C to D, some other non-optimal trajectory from D to B to reach B. There is one single trajectory that is optimal for all points. So, like for example, if you want to walk down the corridor, you can't take a left turn and then take a right turn and then just go there. We all know that we have to move along the straight line at every point of time, so that we need to cover the minimum distance. So this is what the dynamic program principle states, that if we have an optimal trajectory at on at all points on the same trajectory, on all the points of a trajectory, the cost function that we are trying to minimize would be minimum. That means the trajectory is optimal locally too. It's not like we can sum over some two non-optimal trajectory and get an optimal trajectory. The optimal trajectory is one and unique. That is, for each small movement along this trajectory, it has to be optimal. So there is one single unique trajectory that is the most optimal. We can't combine one non-optimal, one optimal, and all that stuff to get to the optimal trajectory. Every trajectory in that, every small local trajectory on that trajectory should be an optimal trajectory. So this is what the principle of dynamic programming say. Yes, I would have been able to illustrate this much better physically, but did you all get this? If you have some background in dynamic programming, you would get this, what I'm trying to say. And please, if you have any doubts, you can answer. You can ask me. So did you all get it?
I think it is clear.
Hello? Yes, I think your voice is breaking.
Yes, clear.
Yeah, you got it, right? Okay. Then I'll clear the frame. So the optimal remains optimal at intermediate. That's what it is saying. So for example, if we are reaching xt, we can't take some other trajectory, then some other trajectory from here in order to get t, and that would be the optimal trajectory. There is one single trajectory, and if we want to reach on an intermediate point, that optimal trajectory would remain the same for that point too. We can't move on a different trajectory for that. This is just an example of a dynamic programming exercise. So now let's get here. That we can incur while going from state A to state B. So can anyone say that can we have more than one value function for a given problem? You can take a guess. Just take a random guess. Can we have more than one value function for a given trajectory?
Yeah, can you repeat that part? Actually, my internet connection was not working properly.
Yeah. Sure. Why not? See, you all saw that notation, right? This is the notation that we are trying to minimize the cost. This is the running cost. This is the running cost, and this is the terminal cost. We want to minimize this cost as a whole, and they have denoted it as JXT. Now, from now on, we will try to define the value function as this: the minimum cost that we can incur from going while going from state A to state B, over the over the domain of all possible control actions. So we'll choose that trajectory which will minimize. That means choosing a trajectory is practically in our control. So practically we'll choose that control which would minimize this cost function. So value function is the cost incurred by our state, that incurred by practically what we are trying to control. For example, the vehicle in that tree case. So it's the minimum cost incurred by your vehicle or by your state in moving from state A to state B. That is the cost incurred on the optimal trajectory. So my question is this: can we have, given a starting point and an end point, can we have more than two value function?
By value function, you mean this expression, right?
Yeah.
No, I
Is
think
the
it should be unique
and can you take a guess on why it should be unique?
because I think our the cost that we have, the two costs that we have, I think they would be unique for a given problem.
Yeah, exactly. The minimum cost would be unique, right? There can't be two minimum costs. There can't be two minimum costs for reaching from state. There might be two trajectories that would minimize. There might be two trajectories that that we can take to get to minimize the cost. That can be there. Again, I'm not sure on this, so I think that would be an open question to everyone. Like, we can have multiple trajectories, but the minimum cost value should always be the same, right? So I think I would need to look upon that. I really don't have much idea whether we can have various different trajectories or not. Like, if you have any counter example, you can definitely give me, where the cost that we are incurring is the same for two different trajectories. So I'm not commenting anything on the trajectory aspect, but we can for sure say that the minimum cost would be one, even though we might reach it in two different ways, three different ways, but the minimum cost is unique. So the value function tells us the value of the minimum cost that will incur for our optimal trajectory over the set of all control actions possible. So this is the value function. So are you all getting it?
Yeah.
Yeah. By the way, I think one line of discourse can be that, for example, like I told you, that the trajectory should always be locally optimal. So if we choose an optimal trajectory, that means it should be locally optimal from one state to the other. So if there are two optimal trajectories, would they be locally optimal? Would both of the trajectories be locally optimal? Like, for example, what I'm trying to say is that there are A to B. This is one trajectory, this is second trajectory, this is third trajectory. We told that if suppose this is the optimal trajectory, on every point, if we want, instead of reaching B, if we divide it into different states and we want to reach that state, that trajectory should always be optimal to reach that state. We can't take a U-turn and reach there, and this would be the minimal one. This trajectory would always be the minimal one. So I would want to listen. I want to have a look at your take on this. Like, can we have two different optimal trajectories that would satisfy this particular dilemma, that it should always be locally optimal, no matter how small the division is? So for each delta time, the trajectory that we're taking is optimal. That means if we decompose the trajectory into n different trajectories, each small trajectory is optimal. So can you say whether we can have two different optimal trajectories or not? I don't think so. We can't have two different optimal trajectories that would specify this, that would satisfy this equation, but I'm not sure. I think you all would need much more context. So was anyone saying anything?
Hello, am I audible?
Hello.
Yes, Athar. Yes, Athar. You are audible.
Yeah. Yeah. So what I'm saying was, I think it's possible. Suppose we take a circle, and
Yeah,
you are at point A. There are 2 points that are across the diameter. So
yeah.
there are two possible ways to get to point B, and
Hmm.
all the points in the path between are optimal too. And you can't take a straight
No,
path. You have to follow along the curve. You can't
no.
go
Again,
straight.
you're imposing constraints, right?
No, but
Yeah,
that
it
is a
will.
problem in itself, right?
Yeah, that is a problem, and in that case, the optimal trajectory is there. So yeah, there are two possible but again, uh, uh,
And actually,
but
I've
are they
uh,
two different
uh,
trajectories though? Like if we set it up in a coordinate system, it's definitely there. But practically, can you differentiate between those trajectories? Yeah, well, you can say that. Yeah, it's in one is in the negative x-axis. Like for example, the second and third quadrant, one would lie in the first and fourth quadrant, one section. So that is definitely there, but that is only there if we apply the coordinate system. On real world control problem, on a real world control problem, can you differentiate between those trajectory?
like real world control problem is not just this in a like car moving, right? It can be anything.
Yeah, it can be anything. Can you differentiate, like in this case, like even can you differentiate? They are practically the same trajectory, I feel.
Uh, I can't give an example right now, but
So you got the point that I wanted to make about the value. Right? It gives us the minimum possible cost that we can incur. Okay. So now, okay, I think this whole exercise, I'll try to do it on the Jamboard itself, the derivation. So for example, so you all saw that expression. I'll write it here too. V value function is practically the integration of C dt. C is the running cost plus the terminal cost. What did it denote it as? Let me just see. Acha, he is denoting it as L. I would denote it as M. L is because they have used the sign distance function, but take it. M is the terminal cost. Okay. Hmm. So this is the value function. No, this is not exactly. This is the cost function. Value function is the minimum value of the cost function over the set of all possible controls. Minimum for the set of controls that we are applying. So you got this, right? Now, what we want to do is that T to T naught, like this is the time over which our control is operating. So we want to operate this. Well, I would, instead of T naught, I would use this. T to T. Instead of, acha, the better thing would be to, instead of using T, I would use 0 itself, like 0 to T. 0 to T is called the time horizon. That is the time for which our control system is operating. This is the time. T can be of any value. In fact, it can be infinitely long too. Ideally, it's not a practical system then. But 0 to T is the operating time or the time horizon of our control system. So value function is the minimum value of the cost function that we have. Till now, I think I'm clear. Now I'll get here now. So can we say for 0 to T? So for example, can we say now, by the way, I just want to be clear. We kind of know the final state that our vehicle is in. Okay. Like at the end of at the end of T, we know our vehicle will end up in state B. We want to reach in state B, state A to state B, and we know that the vehicle is in state B or it's somewhere near. So we know the final state of the vehicle and we know the final state of the vehicle. Where do we want the vehicle in? like what happened during the end of the time horizon. So I just want to give this fact, it would be used further. So according to the principle of dynamic programming, like can we like since the trajectory is locally optimal, can we write this whole function as uh, huh. Acha, by the way, I think I have instead of deriving it, I have actually have an explanation here in this thesis itself. Okay. Can everyone see equation 2.15?
Yeah.
This L,
Yeah.
yeah, this L is this L is practically the running cost. Okay. What they have done is this. Huh. Instead of equation, this would be a better thing to show you. Can everyone see equation 2.10?
Yeah.
Yeah. So L is the running cost here. L depends on the state and U is the control. So the running cost depend on the state we are in and the control that we are applying. S is the time. They are not trying to confuse. So are you getting what this equation is trying to imply? I'll explain it to you. Clear frame. Okay. So what this equation is applying? Okay, sorry. Yes. I mean, I hope you don't mind this many number of times. What this equation is implying. This equation is Vtx, that the value function at time t given a certain state x. Okay. Problem and we'd like to trace it backwards. Okay. We don't know the certain initial state. We want to compute the initial state too, but we know the final state which we want to end in. So from there, we would take an initial value function and then we would try to compute the relevant part of it. So for example, if at the time t plus delta we're in state t, we want to get to know what is the value function at time t. So can we say that at time t, the value function at time t given state x is the value function at this point of time plus the running cost that has been incurred. Okay, plus the running cost that has been incurred from covering this distance. Can we say that? Because the minimum cost the minimum cost over this certain trajectory is the value function at v of t plus delta. Okay, are you all getting it? Hello?
Yeah.
Yeah, can you repeat the last part?
Yeah, I'll repeat the last part. Like we know the minimum cost we have incurred over this particular trajectory, right? It's the value function of v of t plus delta. I mean, we do not know that, but we can we write it as v of t plus delta? Let me erase this a bit. I think it would be a bit more clear once I erase this. Suppose at this is the optimal trajectory, because again we are considering a value function. Make a note that the value function is the cost incurred over the optimal trajectory, that is the minimum possible cost. So I'm just taking that trajectory. I'm not trying to draw all those trajectories now, because I think you must have got it. So t plus delta, t and t plus delta, this suppose our control system is at this state at time t, and at this point in time t plus delta. We know the final value. We know the final value of the problem. Final value in which our, I mean, we know like we technically know the value function at which we are ending. Okay. For example, I think I'm not clearing this point. How do we know the final value function? Okay. For example, in that tree example, what is our goal? Our goal is to not get near the tree. So we want to be in the safe state, that is outside this radius of the circle 0.5. So whatever it is, the final state that we end up in should not be should not be in the safe state, should not be in the unsafe state. So can we say that the value function at time t, at the final time, that is at the end of a time horizon at which we are operating, is this? Can you see what I'm trying to do here? X square plus y square minus 0.5.
Yeah.
Yeah. What? Athar, can you just explain this to me? What I'm trying to do here by this equation?
So we have to stay out of the 0.5 area.
Yeah.
It's a 0.5
Yeah.
radius area.
Yeah. Yeah. Exactly. So, like for example, I'll need to add a minus sign too. We need to stay out of the 0.5 area. So suppose finally at the end of our time horizon, our vehicle ends at this point of time, that is inside this area. That means this whole term would be negative, and adding a term means that the term would be positive, right? Because of the two negative sign, the term would be positive. But suppose we are in the safe state, we are outside the area. What would we want to do? Instead of minus, so this term would be positive, right? X square plus y square minus 0.5. If we are at a distance of 0.7 meter, x square plus y square would give 0.7. Acha, by the way, it should be r square. So it should be 0.25. Sorry. Yeah, and that explains my J rank. So, okay, so we'll try to stay out of this area. This is just the equation of this circle, and we'll try to incorporate it. That's it. So you all are getting it. At the final value function that we are trying to say is try to minimize it, keep it as far as this. So our final value function is this whole function. So if we are at a distance of suppose 0.7 meters, so x square plus y square would be 0.7 0.7 to the power, so 2 whole square. 0.49 minus 0.25, 0.24, and a added minus sign would make it negative. That means if we are outside it, we'll incur a negative cost. That means our cost value would be minimum. But if we get in this point, this whole quantity would be positive. Okay, and we would incur a positive cost, and we do not want that. So we know the initial value function at time. We know the final value function. That means the final state that we want to end up in. That means this should be the minimum value. So we know the final value function, and we want to get back to the value. We want to calculate the value function at each time instant, because as you can see, there is no time. There is no time term here. Okay.
Yeah.
Hello. So you got it. There is no time term in this value function. So now, if we want to calculate the value function, we need to know the time dependence also, right? It depends on time and the state, not only the state. In this case, it's only depending on the state. The time term is not coming here because we have put the value of t here, and t is something which we have put it. So we get it by putting the value t here. So we don't get the time dependence. We want to calculate a time dependent, that is the overall value function. So I think I made it clear why this is a final value problem, because we know the final value function. So can we say like the minimum cost incurred in time t plus delta So for Acha, by the way, you all remember the setup, right? We are at this point in at time t, and we are at this point in time t plus delta. So can we say this? So again, since it is a unique trajectory, that is the value function is a unit quantity. So what would be the value function here? Can we say this? V of the value function would be V
X
of
at t plus delta and t plus delta.
yeah, exactly. So exactly that's absolutely correct, Danish. See, this is the equation. Value of t plus delta and x of t plus delta, the value function plus. So the value function at okay, this is the eraser. So the value function at t plus delta is this. Is the same quantity that Danish told right now, and the value function at t is this. So what is this difference? Can I say that this is running cost between t to t plus delta?
Yeah.
Right. So so does this explain this equation? Equation 2.10. Can you all see this? The running cost between t to t plus delta plus the value function at t plus delta. So now we have decomposed the problem. So so if you remember the dynamic programming exercise, like you must know it better than me, obviously. What we do in dynamic programming is that we have an initial state and then we solve sub problems. I am hoping that I'm correct. So this is that. So the initial state, instead of an initial state, we have a final state. Okay. I think even in a dynamic programming, if you have a 2D problem, something, you can start from this and reach there instead of going from here, right? That can happen. So we have a final state. We know the value function at the final state, some final point. We have it in hand, and we have the system dynamics. So what is our aim? Our aim is to control our aim is to calculate the value function overall. So did you get this equation? Right. So this is the equation that we have. Now I think we can go to the main derivation part. So okay. This is the equation 2.10. Now, do you understand equation 2.15? It's the same equation. Can you see that? Hello?
Yeah.
Yeah.
Can you see that? Yeah, like practically they have integrated it over that delta period, and they have assumed delta to be very small, so they took the running cost over that delta time period as constant and took out the delta term. So can you see this? This is just a simple approximation. Okay. Yeah. So now if you want to get this, so now I think the equation are in order. In now what they are trying to do, like it's clearly written here. We have written the Taylor expansion of this term, v of t plus delta and x of t plus delta. So this is equation 2.16. HOT represents the higher order terms. It's not the hot in a traditional sense, although it is pretty hot out there. So, and when we try to converge towards infinity, but okay. Yeah, so this is the equation that we have. So I hope you all know some basic Taylor series expansion. If you know this, dt represents the time derivative and dx represents the space partial derivative with respect to x, with respect to the state space. So I hope you understood equation 2.16. They have just done a Taylor expansion of this term. Okay, I hope it's fine. And now what they are trying to do, in equation 2.7, we have our state space equation, right? Like what was our state space equation? Achha, does anyone remember the state space equation?
X dot is equal to f of u.
F of x comma a. Okay, that's good. So exactly, I don't even need to write this. You all remember it. Okay, so this is our state space equation. So while doing this Taylor expansion, we get this term delta x, right? Okay. So
Yeah.
so can we write, so we know dx by dt. dx by dt, like del x by del t, I would say dx by dt is equal to f. So can we write dx as f into dt? Right. It's a simple exercise, f into dt. So exactly. So that's exactly what they have done. Just look at this term. They have replaced dx with f into dt. Dt means delta is the change in time. So delta. I hope this is clear. Okay. So what are we getting? V of t plus delta
Yeah,
and
clear.
x of t plus delta is equal to vt xt plus dt plus this term plus this term. Okay. So now if we plug equation 2.17 into equation 2.15, what do we get? This infimum term plus this whole term. Okay. And we want to minimize it over the set of all possible controls. Now, do you notice any control term here in the part that I marked as blue? Can you notice any control term here?
I mean,
No,
the
right?
last term of f of xu.
Only this is the part where we have the control term, right? So
Yeah.
what they have technically done is that they have plugged in this equation. They plugged in equation 2.7, like they have replaced t plus delta by this whole term. Okay. And then taken the parts where we don't have any control term out of it. So this is, so vt of xt can be written as exactly this, right? I think if you're
How
having
did you,
difficulty, yeah.
how did you say that there's no control? Like, how did you identify the last part as a control term?
The last part, see, f of x comma u, this is dependent on the control, right?
Yes.
This is depending on the state and time itself. Like, okay,
Okay.
you can say that the state is depending on the control and all that stuff, but
Yeah,
technically
exactly.
we can't control this stuff exactly. We can change the state and this term would change according to the state itself. We can't use the control and then so the independence is not direct. The only term that we can use for controlling it is this one, right?
Okay, yeah.
Yeah. So this has the u term.
Yeah,
Okay.
yeah, correct.
Obviously. So plugging
Got
it,
it.
and they took this remaining term out. Okay. And use the infimum operator over here. So what can you see here? Can you see that these two terms are practically equal? Okay,
Yeah.
Vt, xt. So that means if we cancel this out, that means do we get this equation? Dt, Vt, xt plus infimum of this term equals to 0. Okay. So do you understand how we are getting to equation 2.19?
Yep.
Exactly.
Yeah.
So now, so this is this is a partial differential equation, right?
Yeah.
Okay. So now to calculate our value function, now we have a particular framework. Now if we solve this if we solve this partial differential equation for v, we'll get the value function, right? Exactly. So this is what we were getting at. So now this is practically the derivation term. So this is practically the derivation of that. I'm not taking too much time. So so now what can we say? That if we solve the partial differential equation mentioned in 2. Okay. This whole term is called Hamiltonian. Are you getting it? I hope you are. So now we get there. So we had this equation, right? Hello? Hi. Now I'm coming to equation 2.42.
Bhaiya,
Now I think, huh.
could you explain whatever you told in the last 2 minutes? I got disconnected. Like, how did you get that
Yeah, no,
Hamiltonian equation?
no,
Hamilton equation.
Hamiltonian, yeah. Did you understand this?
Yes, yes, I did.
Okay. So aren't these two terms the same?
Yep, they are.
So cancelling out on both sides, do we get that the remaining term should be approximately equal to 0?
Yeah.
Yeah. So this is the thing. And this infimum
Okay.
term, that is the this whole term that I'm highlighting is called the Hamiltonian of the system.
Okay.
It's a mathematical definition. We'll have
Mhm.
regarding the intuition, I don't have much clue on how to actually motivate Hamiltonian further. Even I don't have much clue what exactly is Hamiltonian. So it's there. So now let me come to the main part. So it's the P. So this H represents that same thing that I just infimum of LXT over U. That is the Hamiltonian. So now we have a PD, right? Hello. Now we have a PD that satisfies
Yeah.
this equation. Also, can you tell me what this is? This other equation. We have the partial differential equation, and there is the second equation. Can you tell me what exactly is? T is the end of the time horizon. So I remember telling you that there is an initial value function that we are using. We know the value function at time t, at the end of the time horizon. Okay. Like for example, in this case, this Lx was perhaps this Lx was that equation minus of x square plus y square and all that stuff that I mentioned. So what do we have now? Yeah. So now what do we have now? I'll go to the slides and I think the slides are much better there. Optimal control reachability is there. Okay, just a second. So do we have this? So do we have these two conditions? This is practically the computation of Hamiltonian. Do you have these two? Do we have these two conditions? This is the PD. That means our value function should satisfy this PD, and our value function should satisfy this final value condition. Okay. So I hope I motivated these two conditions. These two are the main conditions. Hello.
Yeah.
Did you all get it?
Understand.
Yeah.
Yep.
Yeah.
So in fact, can you give an example where we have a differential equation and where you have a final or an initial set of conditions?
The boundary value problem.
Yeah, obviously, yeah, the boundary value problem. Can you definitely this is a boundary value problem. This is exactly a boundary value problem. In fact, it is a dirichlet boundary value problem. So I'll give you a simple example, not necessarily a final value problem, but I'll give you one thing. Do you remember inductors from your JE days? I think the electrical guys would know it. I want to just clarify it with the CSE guys. Do you remember the inductor equation? LdI by dt.
Yeah.
Yeah. So we have the differential equation LdI by dt plus something is equal to the voltage drop. And suppose if there is an initial current passing through the inductor, we need to specify that current too. Remember it, because the current cannot change suddenly in an inductor. So whatever the initial current was, that time at 0 minus the current at time t equal to 0 would be the same. So for correctly specifying the voltage equation, we would need the initial current through the inductor and the differential equation. So it's quite similar to that, except the fact that we have the final value instead of the initial value. So can you all correlate a bit? It's not exactly that. That inductor equation is a gross oversimplification. Yeah, I think you all get what I'm trying to convey. So this is there. So to solve any optimal control problem, can I say that if I solve this PD itself, if I solve this final value PD itself, we'll get the value function, and then we can decide on the optimal trajectory. Okay. So this is what I'm trying to get at. So this is called the Hamilton-Jacobi PDE. Okay. This is called the Hamilton-Jacobi PDE. The first one, this is the PD itself. This is the boundary condition imposed on it. So this is called the Hamilton-Jacobi PDE, and hence the name of Hamilton-Jacobi reachability. So for any optimal control problem, if we solve the Hamilton-Jacobi PDE, then we can actually estimate the optimal trajectory. In fact, we can identify the optimal trajectory correctly. So I hope till now I'm quite clear.
Yes, please.
Yeah, so it's there. Now, I'd like to motivate one thing. So, yeah. Where do we go now? Like I've derived the PD for you. Now I think, shall I start with reachability now, or I guess the session is long enough. We can keep it as part 1, and then we can keep a part 2 separately on reachability on another day. Would that work? Because again, as you can see, this is only one segment of the part. Now, when I come to reachability, I would need another hour or 1.5 hours, so something. So I would not want to hold you all for too long. So
Yes,
what do you want? Yeah.
Like actually, there
We
are a
can
lot
do
of lag issues today too. So
Yeah, and more than that, the nuances. There are a lot of nuances because till now, I think you all understood the concepts in a broad sense. When it comes to reachability, there are a lot of nuances. Like, do we want to enter the state at a terminal time or at any point of time? Like, I'll give you an example. For example, this there is this tree. That tree example. We apply two set of controls. Suppose we apply this control and we enter the safe state and we get out of the safe state. So finally we were able to avoid colliding with the tree, but we were in the unsafe state for a point of time. And there is a different set of control, for example, where we just take a simple route outside the safe state. What is a better control action?
The second one.
Obviously this one, right? Even though in this case we managed to avoid it, we were unsafe, we were vulnerable at a point, right? So this is a better control action. So for this, so would the terminal condition actually give us a measure of how our trajectory has worked, right? I mean, it won't, because at the terminal state we'll both say okay, man, we were able to avoid it. And okay, in fact, suppose this might be even be farther than this. So this one is there, this one is here. So the value for the cost would be minimum for this one. So we'd say we might say that this is the better control. But obviously we know that this is the better control, that we were never in the vicinity of the tree. So for that, there is a separate set of derivations. In fact, we would just need to build upon the exercise. We can't. So there are a lot of nuances in reachability. Or like, for example, if you don't want to enter the state at any point of time, or we just want to avoid the terminal conditions. So I think it would take 1.5 hours or so. So I would not want to hold you all for too long. And in fact, there is an initial event going on, so you must want to enjoy that too. Today's the last day. So I'd leave you all today. And I hope that whatever I explained today, I think it was quite a mouthful, but I think I was able to simplify up to a certain extent. So there is that. And I was able to motivate some interest. Hello? Hello? Yeah, Athar, go on. Your voice is cutting. I think your voice is breaking. But whatever it is, I'm going to assume that. Yeah, I'm going to assume that today's session was interesting enough for you. That's why you all held for too long, not just because you are all subquads. So yeah, that's there. So I think whatever I've motivated, I've done. So till now I've derived the Hamilton-Jacobi PD. Now I'll give you a flavor of reachability in the next session. I think we can conclude today's session then.